Have you ever wondered why some materials stay magnetic while others lose their strength? To understand how a permanent magnet works, we must look past the surface and peer into the microscopic world of atoms and domains. At the atomic level, electrons act like tiny loops of current. Their spin creates a magnetic moment, effectively making every atom a miniature compass needle with its own north and south pole. In ferromagnetic materials like iron, these atomic magnets don't act alone. They cluster into regions called magnetic domains, where billions of atoms align their magnetic fields in the exact same direction. In an unmagnetized piece of iron, these domains point in random directions. Because their individual magnetic fields cancel each other out, the overall material shows no external magnetic pull. When exposed to an external magnetic field, domains that are already aligned with the field grow larger, while others rotate to match. This unified alignment creates a strong, collective magnetic force. Magnetism is a delicate balance. As we add heat, we increase the thermal energy of the atoms. This causes them to vibrate violently, threatening the orderly alignment of the magnetic domains. Every magnetic material has a specific critical temperature known as the Curie point. At this exact threshold, the thermal energy becomes strong enough to completely overcome the forces that keep domains aligned. Once the Curie point is reached, the material undergoes a phase transition. It changes from ferromagnetic to paramagnetic. The domains vanish, and the atoms point in random directions, losing their permanent magnetic properties. For iron, the Curie point is 770 degrees Celsius. If you heat a magnetized iron nail until it glows bright red, it will no longer be attracted to a magnet, as its domains have been disrupted. Not all Curie points are high. Gadolinium has a Curie point of just 19 degrees Celsius. This means it is magnetic in a cold environment but loses its magnetism just by being held in a warm hand. Mathematically, we track this using the Curie-Weiss law. The graph shows that as temperature approaches the Curie point, the material's ability to be magnetized decreases exponentially until it hits the transition. If the material cools back down below its Curie point, it can become ferromagnetic again. However, it usually requires an external field to guide the domains back into a unified, magnetized state. Engineers use this concept in data storage. By using a laser to heat a tiny spot on a disk to its Curie point, they can easily flip its magnetic orientation to write digital data. Let's test our knowledge. If a material has a Curie point of 400 Kelvin and the current environment is 450 Kelvin, the material will be paramagnetic and will not hold a permanent magnetic field. To summarize, magnetism relies on the orderly alignment of domains. Heat creates disorder, and the Curie point is the breaking point where that order is lost, turning a permanent magnet into a non-magnet. Think about our lesson: what happens to those domains above the Curie point? The answer is C. The domains disappear as thermal energy causes the atomic moments to point in random directions. Understanding the Curie point allows us to manipulate materials for technology and industry. Magnetism isn't just about north and south, it's about the balance of energy. Generated by Vision Solve AI.